Hello, everyone. Good morning. We'd like to welcome you to Pi-thon AU. Yay! All right. So we're going to start this morning with Python teaching math, Python meeting, teaching math with Python. Let's welcome Liam Callaway.
Hi everyone, thanks for coming out to my talk today for the first talk of this session. So first, a little bit about me. Who is this guy? So hi, my name's Liam Callaway. I recently graduated from the University of Tasmania. I'm currently a software developer at WiseTech Global, and in the past I've been a tutor at NCSS, the National Computer Science Summer School, and the University of Tasmania. This is my second PyCon, and it's my first time ever giving a talk, so go easy on me, please. So first of all, just that's a bit about me, a bit about you. Show of hands, who in this room is currently a student, university, high school? Cool. And who's a teacher? Whoa, nice. All right, so hopefully you find this interesting. So I'm going to start this talk with a brief anecdote, as a lot of talks tend to. So last year at the University of Tasmania, I tutored a course called Computational Science. But this course was a bit different because it was actually offered under two separate unit codes with two different titles, the other being Discrete Mathematics with Applications. So this course covered a lot of sort of first year maths concepts with set theory, combinatorics, number theory, but it was also supplemented with practical implementations taught in Python. And the content was exactly the same for both unit codes. So this meant that students studying a programming degree were doing the same assessments as students studying a mathematics degree. They had lectures for both maths and programming, assignments for both maths and programming, and tutorials for both maths and programming. So I was taking the tutorials and the lab sessions for the programming content, but I got to interact with students from both streams. And I would get this question a lot from the programming students. Do I have to learn maths? I want to be a programmer. Maths is hard. Why do I need to do this? Maybe not always quite negatively. Sometimes these questions were genuine, coming from like, I'm scared. Is this something that I'm going to need to be good at my job? But then from the maths students, do I have to learn programming? A lot of these mathematics students were taking a programming course for the first time, and this was all completely new to them. So to answer these questions, I would usually say, no, you don't need to learn these things, but you should. And this course is a pretty good way to get started with it. So Python's pretty great, right? We're all here at PyCon. I don't think I'm going to have to try too hard to convince you of that. There's lots of really good reasons that Python is a useful language. It's very clean and expressive. Because it's interpreted, it makes it highly interactive. And its batteries included. We have a lot of useful tools through the standard library. And in fact, you might be familiar with something called the Zen of Python. These are some design principles that Python is built around. If you open up a Python interpreter and type import this, you get a whole list of these. And I've pulled out a few here. We have things like beautiful is better than ugly, sparse is better than dense, but readability counts. But the reason why I've selected these here is because I think that these are some good examples for mathematics as well. If we're doing a proof, we want it to be beautiful and simple rather than ugly and going on for pages and pages. But then at the same time, we don't want to make things too dense because readability counts. Also, I actually studied an applied mathematics degree rather than pure maths, so that last one, practicality beats purity. So this leads me to the conjecture that getting hands-on with Python is a great way to learn some maths. But also, getting hands-on with maths is a great way to learn some Python. So for the rest of this talk, I'm going to run through some examples that I think illustrate this concept, how we can introduce some mathematical concepts alongside programming concepts and use this bridge to sort of extend both topics. So first, let's talk a little bit about set theory. Yes, this talk will feature memes. So what is a set? A set is a collection of objects that belong to some group. They're defined by a certain property or attribute. The elements of a set are unordered, and we don't care about repetitions within a set. In maths, we have a few ways of notating out a set. We have something called list format, where we simply list the values. But more commonly, we use something called defining property format, where we have some function which defines our set, and then some range of values that our set can take. So that's all well and good. How do we do this in Python? Well, Python also gives us a few different ways of defining a set. Again, we can simply list the values using what's called a set literal with the curly braces. But we also have something called a set comprehension, which, just like defining property format, allows us to create a set using some generating function and some range of values for that to take. So this is a concept that students that maybe have a bit of programming experience before but are new to Python might take them a little bit to wrap their head around. They're used to the sort of traditional looping structure. But for mathematics students, they're already used to this kind of notation, and we actually found that a lot of them pick up this idea a lot quicker. So that's quite neat. It also, in Python, if you want to create an empty set, unfortunately you can't just use the empty set literal like that, because Python is going to interpret that as a dictionary. So you have to use this set constructor instead. So now that we've got some sets, what can we do with them? Well, this brings us to set operations. And set operations are really just about allowing us to answer specific questions about groups of things. So we could use set operations to see who has attended either PyCon AU or LinuxConf, or even things like how many people came to the keynote this morning but forgot to bring a coffee. So I'm going to run through some of these set operations really quickly. First of all, we have set union. This is the elements that are in either set A or set B, and we denote it with this little U symbol. Conversely, we have set intersection. So this is the set of elements that are in A and B, and this is notated with the upside down U symbol. And set difference, the set of elements that are in A but not in B. So now that we've seen that, how do we do this in Python? Well, Python gives us this nice, clean, readable function notation. We have two sets here, A and B, and we simply call the corresponding function on one set and pass it the other one. And you can see these results here. So it's really obvious what we're actually doing here. A union B, A difference B. But Python also gives us another way that we can do this using what's called the operator notation, where we replace those functions with single character operators. So for union, we have the vertical bar character, intersection has an ampersand, and difference is subtraction. So at first glance, you might think that this is actually less readable. It's not as clear what's going on here. But this is still useful to know, because this operator syntax is actually closer to what we're going to be doing in mathematics. In maths, we're used to this idea of having two objects with an operator in the middle of them. But what's more, this actually suggests a really useful conceptual link to other topics like Boolean algebra and logic. You saw that for a union, we use the vertical bar character. Well, in Boolean logic, that's an OR symbol, and the union of two sets is the element in A or B. So that we can start extending some of these ideas and linking them to other topics. And then on top of that, we can also start looking at some more advanced computer science topics, talking about things like operator overloading. How is this actually made possible? And in Python's case, that's using the double underscore methods. There's a bunch of other Python set operators as well that are built in, things like subset and superset, or symmetric difference, which is the equivalent of a set XOR. Another useful thing we might want to do with sets is do membership testing. We want to determine if an element belongs to a set or not. So in Python, we just use the in keyword. We've got a nice readable way of doing this as well. We can say, is the element 4 in set A? So this is really simple. Python makes it nice and clean and readable. But again, there's opportunities for further discussion and exploring these topics. How long does this take to run? What if this set is really large? Well, then we can start talking about things like linear search or binary search. But of course, these are a set. So these are actually going to be backed by hash sets, which are a more complicated data structure. But these have interesting properties because they're storing the elements not in the order that they're added, but based on their hash values. And now our Python sets have a lot of the same properties as the mathematical definition of a set. The elements are now unordered and we can't have duplicates. But now we can also start talking about how sets give us instant lookup with O1 runtime complexity, and what does that actually mean? What is big O notation? So that's a crash course in sets. Next up, combinatorics. This one's bothered me for ages. Permutation log, clearly. All right, what's combinatorics? Combinatorics is all about different ways elements of a collection can be combined, hence combinatorics. We have many intuitive real-world examples for combinatorics, which makes this a lot easier to sort of talk about and explain, but it's also highly relevant to a number of important computer science problems. A lot of these have ongoing research. And like lots of fields of mathematics, it actually builds upon and links to lots of other disciplines. So the bread and butter of combinatorics are permutations and combinations. So given a collection of items, how many ways can we select a subset of them? And does the order matter? If we care about how we're going to order them, it's permutations, otherwise combinations. So permutations often conceptualizes how many ways can we arrange n items. So this could be something like the books on our bookshelf, or classes in our timetable, or the numbers in our PIN code. Now there's a formula given for calculating the number of permutations. We have this n factorial over n minus k factorial. Now, I'm not going to sit here and talk about equations, or talk, but this is going to come back later, so just keep that in mind. Now, combinations, otherwise conceptualized as how many ways can we choose n items. So now we don't care about how we order them, we're just selecting them. So for example, which books would we feature in a catalogue, or maybe picking out our lottery numbers. The gambling is bad, so don't do that. And again, we have a similar formula for the number of combinations. You'll see here that this actually has an extra k factorial term on the bottom here of the fraction. And what this tells us is that the number of combinations is always going to be a lot less than the number of permutations, because we don't have the option of rearranging them to generate extra permutations. So in Python, we're going to be using the IDA-tools module. Now, IDA-tools has a bunch of different tools for efficient iteration, but in particular for our case, it has built-in functions for calculating permutations and combinations. So if we're teaching this to a student, we might give them an example like this. All they need to do is import permutations. They create some collection of things they want to permutate, in this case, subjects, maybe for a timetable, and they run this permutations function. And they go, great, that's worked, let's print out the result. And we get this IDA-tools.permutation object. So many questions. What is this? What is going on? Why didn't my program work? Well, it did, but clearly something more complicated is going on here. And I'm a tutor, I have a class of 20 kids. I kind of have to tell them, well, for the moment, we'll come back to this later, but just convert it to a list. And then you can print it out, and we'll see all the values. This is going to bite me later. And similarly for combinations, just instead of importing permutations, we import combinations. So you can see here we have a different collection of fruits. What two different fruits could I take maybe from morning tea before? So you can see we have an apple and a banana, but not a banana and an apple, because they're the same combination. So let's run through a practical example of a question that a student might get on an assignment. How many 8-character passwords are possible using only the lowercase alphabet without repeating a character? All right, so we need to think, is this permutations or combinations? The order matters for a password, so it must be permutations. So the student's seen some examples. They might start out with some code. We give them the lowercase alphabet. They get the permutations function. Lowercase letters, how many ways can we pick 8 of them? And then we need to see how many, so we use the len function. And we get another error. Object of type IDA-tools permutation has no len. Why? Why won't it work? Well, some of you in the room probably know exactly why it's not going to work, but the student didn't. But the student, who did pay attention in class, remembered that I told them to just convert it to a list. Now, this is actually, this code is running, so I have to comment this out, otherwise my talk would end here. Nothing but sadness awaits. So why didn't it work? Well, remember, this is our formula for calculating the number of permutations, n factorial over n minus k factorial. So let's substitute in our values for n and k. We have 26 letters, selecting 8 of them. Let's evaluate some of these permutations. We see we have 6.3 times 10 to the 10. That's 63 billion possible passwords. Quite a lot to deal with. So what do we learn from this? Well, clearly, factorials get really big really quickly. And again, now we can start talking about runtime complexity, and also in this case, memory usage, and why these two things matter. Now, we had that IDTools permutation object before. Well, that was a generator. And generators are a really cool, interesting concept. And we can start talking about these and the problems that they solve and how we can use these tools to get around things. But we don't actually always need to rely on generators to solve these sorts of problems. Sometimes we should just go back to the basics. So let's take another look at that question. How many 8-character passwords are possible? It didn't ask us to generate those passwords, and it definitely didn't ask us to store them in memory. Okay, once you give students this tool of being able to generate these permutations and show them how, they're going to want to do that. But you don't actually need to do that for every question. Sometimes it's just a matter of doing the maths. Now, of course, calculating 26 factorial or whatever by hand is a bit tedious. Maybe you don't have a scientific calculator on you, so we can just use Python again. Unfortunately, the Python doesn't have a built-in factorial function, but we can import one from SciPy, put in our values for n and k, and we see our 63 billion passwords with a little bit of floating point error. But, don't worry about that. Okay, next up, linear algebra. So I contemplated whether or not leaving this section in, because it's actually really hard to talk about linear algebra in a few minutes in a talk. But the reason I left it in is because I think it's a really good example of how we can start thinking about algorithms. So, linear algebra, matrices. What is a matrix? Matrix is a two-dimensional array of elements. Here, the positioning within a matrix does matter. And matrices are actually a different type of mathematical object. So we have standard operations defined, but they might work a little bit different to what you're expecting. Now, if we're going to do anything with matrices in Python, chances are we're going to be using NumPy, because it's a really core library for scientific computing. It has, amongst a bunch of other tools, a really high-performance n-dimensional array object that we can use for doing matrix operations. So let's start playing around with NumPy. If we want to construct some matrices, we just import the matrix constructor, we pass it a list of lists, and we get these two matrix objects out. Let's do some addition and subtraction on them. So for addition and subtraction of two matrices, you simply add up the elements in the corresponding positions. So this means the two matrices need to have the same size. You can see for addition, we have in matrix A in this position 2, and in matrix B this position 3, and our result is 5. But if we were to subtract them, our result is -1. All good so far. What about matrix multiplication? Well, clearly it wasn't going to last. Something different is happening here. 2 multiplied by 3 definitely isn't 9, last time I checked. But also you'll see that the results for this is actually different if we flip the order, because matrix multiplication is actually defined differently to addition and subtraction. So this is where I try and teach you matrix multiplication in 30 seconds. No, that's not going to happen. Okay, so this is how we might teach it to a mathematics student. We've got some nice formula for how to define matrix multiplication. But if you're a first-year computing student who doesn't really like maths, this stuff is scary, right? What's this thing? This is like a sum or something? I don't... How about an algorithm? All right, we like algorithms. Algorithms are fun. They tell us what we need to do. They're a recipe. Turns out actually writing matrix multiplication in an algorithm is also harder than I thought it was going to be. But this is my attempt at it. So if we're multiplying two matrices together, C equals A times B, we iterate over the rows and columns of C, and what we actually do is we get the corresponding row from one matrix and the corresponding column from another matrix, and we multiply each element pairwise and sum them all up like this. So for this position, we're using this row and this column, and for this position, we're using this row and this column. All right, that's my 30-second explanation of matrix multiplication. But we've got this algorithm, so now let's do it in Python. And you can see that the code for doing this in Python is pretty much just that algorithm that we had before. Hint, I wrote the Python first and then, yeah. Okay, so the only extra thing we need to do is sort of calculate what our values for the rows and columns are and sort of initialize our matrix with a bunch of zeros to start with, and then we can sum them up. There's a bunch of different ways to do this. There's better ways to do this, but this is one way. And now we can do matrix multiplication with just two lists of lists. We don't actually need the NumPy matrix constructor. And we can see that we get the same results that we had before. Admittedly, they're not formatted as nicely. So why? Why, Liam? You just told us you can do this with NumPy. NumPy's going to do a better job. Why not just use NumPy? Well, this gives us a better understanding of how matrix multiplication actually works. Because remember, the students that are studying this also are going to have to do this on written maths assignments, okay? And if you're a programming student who's new to this, getting any sort of practice of sort of conceptualizing this idea and the steps that you need to do is really useful. And this gives us practice in doing that. And we're breaking down a process and actually implementing an iterative algorithm. And again, this also gives us a sense of why matrix multiplication is a really computationally expensive task. Even though it's so important, you saw we had those 3 nested for loops before, so we have a classic example of an O(n) cubed algorithm. So what does that mean? And are there ways that we could maybe do it better? Turns out kinda, but not really. And we can make a similar case for matrix determinants. This is another calculation you can do on a matrix, which sort of reduces down to a really simple recursive algorithm. Well, moderately simple recursive algorithm. So now that we've done this matrix multiplication, let's take it further. Let's practice some OOP. So we can actually create our own matrix class like this, and using the _mul method for overloading matrix multiplication, we can just insert our code from before. We can also do the same for an add method and a subtract method, etc. And we can create our own matrix class and do some of those operations that we saw NumPy doing ourselves. So now we've got an introduction into OOP. All right, my last set of examples are all about visualization and data. So Digital K did a talk yesterday in the education track, and she had a bunch of great examples for this. I was really impressed to see those as well. So some of these might be a little bit familiar, but I'm going to go through them really quickly. If you're interested in this stuff, I'd really recommend watching her talk. It was fantastic. So first, I just want to talk briefly about Jupyter, or as it used to be known, IPython. So Jupyter is a web-based notebook which allows students to prepare documents which contain both live code snippets and rich text to annotate them. So this is really useful if a student is preparing some sort of report or presentation and they need to include code in it. And that code is actually runnable. Now, what you might be surprised to learn as well is that these slides that I've prepared today were actually all written in a Jupyter notebook as well, and then it's a little simple extension to convert them into slides. So this can be a really useful tool in some of these sort of situations. So my next few examples about how we can sort of do some visualization and plotting with Python all use the matplotlib library. Now, in these cases, the code itself is not particularly interesting or relevant to the talk, so don't get too bogged down in what's happening there. How this is useful is that a student or a tutor can prepare this sort of boilerplate code and provide it to students to allow them to experiment. So I've got 5 minutes left, so I'm going to rush through these. We can plot functions really simply. We just create our x-axis and a y-axis using matplotlib and NumPy, and we can simply show a nice, beautiful sine wave there. Similarly, we can do the same with charts and graphs. We just get our x-axis and some y points here, and we can see a nice bar chart. So maybe we've done some data collection in class, and we want to plot that into a bar chart. Let's get a little bit more fancy. Let's do a linear regression. So here we've got a bit more boilerplate here. I've got a function to calculate a line of best fit. Now, of course, I'm not doing that myself. I'm using the stats function, the stats module from SciPy. And then we can just do a linear regression plot like this. So you can see here now I've got some x and y data points, And I just call that function, and we get our nice blue data points with our line of best fit through the middle. Let's get even more fancy, 3D surfaces. These are really cool. So you saw before with the function plot we had of a function with one variable, y equals x. Well, if we add another dimension to that, we have something like z is a function of y and x. Now we take it into 3D. So again, a little bit of boilerplate here. We have this apply function, which is going to map a function onto that 3D space, and then do our plotting here. Again, not too important. Don't worry too much about this code. I can show you later. But what we can do is define some functions. So I have one here called a saddle, otherwise known as a hyperbolic paraboloid. I think it just looks like a Pringle. And we can plot that with some x and y ranges here. But you can see I have another function here which is a little bit more complicated called a sync function. And I can just change this here, run that, and we see we get another 3D plot there. All right, so summing up, pun intended. Look, I said at the start, I like bad jokes. All right, so I really think, based on these examples, we can see that learning programming alongside mathematics can be used to sort of help bridge these related concepts. If we have students familiar with one stream or another, they can sort of use that as an entry point into start exploring the converse. Both of these fields contain a lot of opportunities for further extension and inquiry. Once we get started, it's easy to use these tools to sort of start stepping through some more complicated ideas. And clearly, Python is a fantastic tool for introducing these concepts to new students. As you've seen, all these built-in libraries provide plenty of useful tools. Because it's interpreted, we're dealing with a lot of interactivity, and this allows students to really experiment. You saw I could easily change that example of a 3D surface plot before. And of course, Python's simple, clean, and readable syntax is really going to lower some of those barriers to programming. There's been lots of talks about this already in the education track. But where I find this is useful is that it allows students and tutors and teachers to focus more on the important concepts that they're trying to convey. We're not getting too bogged down in syntax and other things like that. And instead, we can actually start talking about things like calculating permutations and runtime complexity or using hash sets, things like that. So, thank you very much for listening to my talk. The slides are available online through this tiny link. They're on GitHub. You'll actually see that Jupyter notebook. So you can also look at all the code snippets there. Do we have time for questions? No. Okay. So thank you very much. If you're interested in this, any questions, I'll be milling around. Feel free to come up and talk to me. I'd also love to hear if you have any comments about anything I've said, because these are just my opinions. As students, teachers, or other developers, I'm curious to see what you have to say. Otherwise, thank you.
Thank you, Ian. All right, so as he said, we would ask that if you have questions for Liam, you take it out to the hall as we have 10 minutes until our next